Assalamualaikum warahmatullahi wabarakatuh. We are from S11431. We'll introduce to the guests about the effects of shift equilibrium on a carbonated drinks. So, let's go. So, here are our members, which are Qayyim, Ainul Shafiyah, Batrisyia Akhtar, and Syazwana. So, we will talk about the introduction, application, importance, conclusions, and reference.
Introduction. Chemical equilibrium occurs when a chemical reaction reaches a balance point. At this point, the concentration of products and reactant stay constant over the time because the rate of the forward and reverse reaction are the same. Le Chatelier's principles. If a system is exposed to a stress, the system will shift as to relieve that stress. Three primary factors that involve in chemical equilibrium. First, the changes of concentration. Second, the temperature, and last, the pressure.
Now, let's move on to the next slide. I will talk about the application of shift equilibrium in carbonated drinks. The concept of shift equilibrium applies to carbonated drinks through a process known as carbonation. Carbonation is the process of dissolving carbon dioxide (CO2) gas into a liquid, typically water, to create a fizzy or bubbly beverage. During carbonation, CO2 gas is dissolved in the liquid under high pressure. This creates an equilibrium between the dissolved CO2 molecules and the CO2 gas in the headspace of the can. The equilibrium is maintained by the balance between the rate of CO2 molecules leaving the liquid and the rate of CO2 molecules entering the liquid.
If we shake a bottle of soda, it fizzles and bubbles. The bubbles are actually carbon dioxide gas that dissolves under the liquid, as in the soda. When the soda bottles are opened, the volume are increased. This is due to the increase of volume of air getting into the bottles. When the air is getting into the bottles, the pressure are reduced. When the pressure become low, the molecules of CO2 are no longer frequently colliding with each other. To cope with this, more CO2 is produced so that they will collide more with each other to counteract the low pressure. So, the reaction side to the side with the more mole of gas, which is to the right.
Hello, so now I will talk about how temperature affects the bubble or fizz formations in carbonated drinks. So, fizz is caused by dissolution of CO2 carbon dioxide in a liquid. Higher concentration carbonic acid means more CO2 dissolved in water and greater fizz. If the temperature of a room temperature soda is increased, the equilibrium will shift to the left. This is due to the exothermic reaction of producing CO2 gas and will release heat to counteract the high heat. This favors decomposition of carbonic acid, thus reducing its concentration, releasing more carbon dioxide gas to the air. So, the soda is less fizzy. So, this is the chemical equation between carbon dioxide and water, and it forms carbonic acid. H2CO3. Next, if the temperature is decreased according to soda, the equilibrium shifts to the right, favoring the formation of carbonic acid because it is an endothermic reaction and will absorb the heat to counteract the heat loss and increasing system temperature to reach an equilibrium. Higher carbonic acid concentrations results with more dissolution of CO2 in a liquid, thus the soda is more fizzy.
There are three importance of shift equilibrium. First, by manipulating the conditions to favor the formation of products, we can increase the yield of desired products in a reaction. This is crucial in industrial processes where high product yields are desired. Next, shifting equilibriums allows us to control the direction of a chemical reaction. This is useful in reversible reactions and help us to produce specific compounds as well as avoid making unwanted byproducts. Lastly, by studying the factors that affect equilibrium, we learn more about how chemical reactions work. This helps us predict and analyze reactions in different situations.
In conclusion, the carbonation of water and the release of bubbles when the beverage is shaken exemplify the principles of chemical equilibrium, specifically the dynamic balance between dissolved and gaseous carbon dioxide. Understanding this equilibrium dynamics enhance our application of the behavior of gases in liquid and has practical implication in the production and enjoyment of carbonated beverage.
These are our reference